Next, we're going to talk about a result called the chain rule. Now, we've learned many derivative formulas, and with those we could take certain derivatives. But they are somewhat, well, we are somewhat restricted in which functions we can take derivatives of. So, for example, we can take the derivative of sine x using that chart, and the derivative is cosine x. But we can't yet take the derivative of something like sine of 2x, where in here we have more than just an x. All of those rules, those 22 rules, apply with just an x on the inside. Here we have a 2x, and we can't take that derivative. But using the result called the chain rule, we can. So let's write down the chain rule. The difference between sine of x and sine of 2x, well, one difference is that you can break sine of 2x into two functions. And sine of 2x is actually a composition of functions. And the chain rule tells us, well, a composition of functions, remember, looks like this. F of g of x. And the chain rule tells us how to take the derivative of this. And the rule says that this derivative, the derivative of the composition, is f prime of g of x. So we have an f and a g. The derivative is f prime. Leave the inside alone. And then multiply by g prime of x, the derivative of this inside function. So for example, with that example, sine of 2x, the derivative of sine of 2x, well, here we have an outside function and an inside function. The outside function is sine. So for the first part, we need the derivative of sine, which is cosine. We leave the inside alone, so the inside here is 2x. We leave that alone, but then we multiply by the derivative of that inside. The derivative of 2x is just 2. And we could rewrite that. Sometimes it's nice to simplify these, sometimes it's not. With something like that, I think it's nice to just throw the 2 out front. So the derivative of sine of 2x is cosine of 2x times 2. Derivative of sine is cosine. Leave 2x alone, and then multiply by 2. Now, certain compositions aren't immediately obvious. At least I don't think certain compositions are immediately obvious to see. So there is an alternative notation we could use for the chain rule. We can introduce another variable, and even though we will introduce another variable, in some ways it makes the composition or the computation a little easier. So we'll say alternative notation. Now let's spell notation correctly. For the chain rule, says that given y equals f of x, the derivative of y with respect to x, introduce the variable u, is the derivative of y with respect to this new variable u times the derivative of u with respect to x. So in particular, we're introducing u as a function of x. And we'll see an example of this in a moment. But first, right here, this derivative notation looks like a fraction. And right here, with this result, it kind of looks like you would expect, because in a fraction, if you multiply and divide by something, they go away, they multiply to 1. And right here, you can sort of see on the right that this looks like a fraction dy dx. Now, these derivatives are not fractions. Sometimes they behave like fractions. And sometimes it's useful to have sometimes it's useful to use fractions to show that behavior. Right here is one example. Now, this is not always the case that it behaves like fractions. In this example, or in this statement of the rule, works like a fraction because in Calculus 1, our functions are all functions of one variable. In, for example, a Calc 3 class, you'll have functions of two variables. And the chain rule in Calc 3 does not look like, the result for the chain rule in Calc 3 is not consistent with the fractional behavior. But right here, in the back of your minds, you can think that this notation is useful because it allows us to compute derivatives using, when I thought of this, or when I first did this, I thought of it like this with the fraction canceling, and I knew in the back of my mind that they weren't actually fractions. So before erasing that, let's just show how we would do a computation like this, or with this notation. You'll always have y as a function of x, and here we need to introduce another variable u. So let's say let u equal 2x. Let u be the thing that's preventing us from applying one of the initial 22 derivative rules. Well, to find dy dx, which we want to find, we need now dy du and du dx. I'm going to write let u over here, actually. Let u equal 2x, and write that over there. Now du dx we can find right away. Du dx. And that's just 2. Dy du, well, let's substitute u in here, because we're replacing all of these x's with all the 2x's with u. So now y as a function of u is sine of u. So dy du, our variable is now u. The derivative of sine of u with respect to u is just cosine of u. So now if we want dy dx, so dy dx is dy du, cosine of u, times du dx times 2 equals cosine of u times 2. And we don't want u's in our answer because our variable here is x. So we'll just replace u with whatever it is in terms of x. And then times 2. And you could write that as 2 cosine of 2x. So with these derivatives, you could write out a u substitution, or you could do it like we did the first example. When I first learned it, I definitely did the u substitutions and wrote them out. As I did more of them, I stopped doing that. But for some of the examples we do today, I will write out the u. For some of them, I won't, and I'll just explain through it. So let's look now at this function. And all of these, the directions are going to be find dy dx. So example, find dy dx. Y equals all of this to the 10th. Now there are two ways we could do this. We could draw Pascal's triangle, find the 11th row, expand that, write it as one polynomial, and then take the derivative using a bunch of power rules. Or we could use chain rule. Now how do we use chain rule? Well, we're going to let u be this entire inside quantity. And if we let u be that entire inside quantity, then y is just u to the 10th. And to find the derivative dy dx, which we want, all we need to do now is find dy du and du dx. Dy du, that's just a function to the 10th. Derivative of a function to the 10th is, or of a, well, variable, let's say, to the 10th with respect to that variable, using power rule, is 10 of them to the 9th. We also need du dx. Well, the derivative here with respect to x, that's just a polynomial. We'll use a couple power rules. 3x squared. X squared. Negative 5 times 2x, also known as negative 10x, plus 0. And then dy dx is just these things multiplied. So we have 10x cubed minus 5x squared plus 7 to the 9th, 10u to the 9th, but we're going to substitute this back in by the end. So I'm just going to do that substitution now. Dy dx is this times this. Substitute x cubed minus 5x squared plus 7 in for u. Dy dx is 10u to the 9th. Times du dx. So we have dy du, du dx. Now, I'd just like you to observe how we could have arrived at this answer without going through the substitution, because it is worth making this observation. What is this function y? What is this function y? This function y is something with x's all to the 10th power. Something with x's all to the 10th power. Something with x's all to the 10th. Well, if we want the derivative, we can do that by using the power rule. 10 of them to the 9th. That's what we have here. 10 of them to the 9th. But then the chain rule says that you have to multiply by the derivative of this inside piece, meaning this inside piece. We have 10 of them to the 9th, the derivative of them, 3x squared minus 10x. So if you start with a function to the 10th, well, you can take its derivative by doing 10 of them to the 9th, and then multiplying by the derivative of that inside. Let's do another. Find dy dx here. Y equals sine of 5x squared plus 7x to the negative 4. Now how can we do this derivative? Well, let's remember what happened when we did y equals sine of 2x. To find that derivative, this is a sine function. Derivative of sine is cosine. And then we multiplied by the derivative of this 2x. Derivative of sine is cosine. Leave the inside alone. Multiply by the derivative of that inside. Well, we're going to do the same thing here. We're going to do the same thing here. This is a sine function. Derivative of sine is cosine. But the chain rule says you then multiply by the derivative of that inside piece, which in this case is what? 10x negative 28x, and then negative 4 minus 1 is negative 5. So we have a sine function. To start with, the derivative of sine is cosine. Leave the inside alone. Multiply by the derivative of that inside. If you wanted a u substitution, since it's a sine of something, the u substitution would be u equals that inside. You'd get what y equals sine of u, dy du is cosine of u, du dx is 10x minus 28x to the negative fifth. So dy dx is those two multiplied together with the x's substituted back in for u. Notice when I said there du dx was whatever it was, I looked over here. Next, find dy dx. Y equals secant x plus cosine x to the negative third. Let's do the u substitution here. Right here, this function is something to the negative third. Something to the negative third. So we're going to let u equal that something. So dy du, well, what's y as a function of u? U is that thing, so y as a function of u is just u to the negative 3. dy du, negative 3u to the negative 4. And du dx, what's du dx? Well, we have secant x plus cosine x. Derivative of secant is secant x tangent x. Right here, notice, we didn't have to use chain rule to take the derivative of just this secant x, because the variable here is only x. And similarly, for cosine x, you don't have to use the chain rule to take the derivative there. Derivative of cosine is just negative sine of x. So we have dy du and du dx. So dy dx is those two multiplied. Dy dx is dy du du dx. Dy du is negative 3u to the negative 4 times du dx. And you don't have to simplify. Let's erase this substitution and talk for a moment about how we could have gotten to that answer without the substitution, or without writing the substitution. This is a function to the negative third, so its derivative is negative 3 of them to the negative fourth times the derivative of this inside function. Secant x tangent x, negative sine x, from the 22 derivative rules. My eraser's not erasing all that well today. I'm going to have to get another one. How about this one? Y equals the square root of x squared plus 3x. Well, when we're taking derivatives of square roots, we could remember what I said at the end of the derivative video, where I said the derivative of root x is 1 over 2 root x. Now, when we're actually doing things with derivatives, that observation will become useful. For just finding the derivatives, you could use that. I sometimes do, but I won't for this example. And what I mean by that is I'm just going to use a power rule directly. by writing it as x squared plus 3x to the 1/2. Now, how do we take this derivative? Well, we know how to take the derivative of something to the 1/2. So let's let that something be u. Let u be x squared plus 3x. Then y is u to the 1/2. So then dy du is a half u to the negative half. From the power rule, bring down the half, u to the half minus 1. A half minus 1 is negative a half. If you have 50 cents and spend $1, you are down 50 cents. And du dx is 2x plus 3. So now dy dx is these two multiplied. And I'm not going to simplify this, I'm just going to write out the multiplication. Later in the semester, maybe next week, weeks after that, I might simplify the square root ones a little, but for this one I'm not going to. So dy dx is these two multiplied, half u to the negative half, u is x squared plus 3x, so half u to the negative half, times 2x plus 3. And as an observation, let's look at the original function and compare it to that answer without any u's written and without any intermediate steps written. We have a function to the 1/2, so its derivative is half of them to the negative half times the derivative of the inside. When thinking of these functions, I almost never actually think of the composition in terms of f and g. Well, I said almost. I'm pretty sure in, how many years have I been knowing chain rule? 10 years? In 10 years of knowing chain rule, I'm pretty sure exactly 0 times I've thought of it with f and g. Many times I think of it with a u. But almost always I think of it as an outside function and an inside function. Here, the outside function sine, the inside function is 2x, and the derivative is given by the derivative of the outside, leaving the inside alone, and then multiplying by derivative of the inside. Next, how about this one? Find dy dx. Cosine to the 4th of x. Well, what is this function? This function, cosine of x to the 4th, cosine to the 4th of x. This is a function all to the 4th power. So it's a function all to the 4th power. And if we want the derivative, well, we can write that function to the 4th power as u to the 4th by letting u equal cosine of x. Well, now, this says then whenever I write it over here. Sometimes when I write then, it looks like a capital T with almost no letters written afterwards. Then, dy du, well, that's just 4u to the 3rd. dy dx, or dy dx, du dx, since u is now a function of x, is what? Derivative of cosine, negative sine. So let's combine this answer, and we can find dy dx. I really should be writing a then over here too, but I haven't done. Dy dx is 4u to the 3rd. U is cosine, so 4 cosine to the 3rd times negative sine of x. And I guess we could simplify this a little. we could, if you want, just take that negative out and write that cosine to the third in the other way of writing cosine to the third, or you could leave it as that first answer. So here, we started with a function to the fourth. Started with a function to the fourth, and we have 4 of them to the third times the derivative of that inside function. Next. What's a good one next? We've done some trigs and powers. Let's do this one. Cotangent of cosecant of x. Cotangent of cosecant of x. So when I look at this function, my first thought is this is a cotangent function. It is the cotangent of something. What's that something? Well, let's call it u. U is now cosecant of x, and the original function is cotangent of u. And now we can take these derivatives using the 22 rules. Cotangent of u, the derivative of that, is negative cosecant squared of u. Sometimes if it's just an x or one variable, like a u, sometimes I don't write the parentheses. Sometimes I do. As you can see, sometimes I do, sometimes I don't. Dy du, negative cosecant squared. Du dx. Well, the derivative of cosecant is negative cosecant x, cotangent x. Well, and then dy dx is just those two things multiplied. Those two things multiplied, there's a negative here and a negative there, so I'm not even going to write the negatives. So cosecant squared of u, what's u? U is up here. So it's negative cosecant squared of cosecant of x. With these, it's sometimes useful to draw the parentheses pretty large to help keep yourself organized. So just with the substitution, we have negative times negative is positive, so we have cosecant squared of u, which is cosecant. So you have cosecant squared of cosecant times that. Times cosecant x, cotangent x. And this is not cosecant to the third. This is also not cosecant to the fourth. This is cosecant squared of cosecant times cosecant cotangent. And again, let's compare this answer to the initial function. And how did we get this answer? Or how would we get this answer without the substitution? Well, a cotangent function, the derivative is a negative cosecant squared. Leave the inside alone. Multiply then by the derivative of the inside, which is negative cosecant cotangent. So the two negatives go away. Derivative of the outside is negative cosecant squared. Leave the inside alone. Derivative of the inside, negative cosecant cotangent. Let's do another. Let's do, before we do exponentials and logs, let's do this one. did a cotangent. Let's not do another cotangent. What did we not do? We did not do a secant. Well, here, what is this function? This function is not like something to the fifth. This function is a quotient. And we know how to take derivatives of quotients. So let's start by taking the derivative of the quotient. We use the quotient rule. Leave some space for some side work in a moment. But for now, we're doing the quotient rule. What's the quotient rule? Derivative of quotient is bottom derivative top minus top derivative bottom over bottom squared. So what did I say? Bottom. Let's write bottom. Bottom is secant of 3x. Derivative of the top. I'll leave it as a 4. So we have bottom derivative of the top. We haven't used a chain rule yet. Bottom derivative of top minus top minus top minus top derivative of the bottom. Well, the derivative of the bottom is the derivative of secant of 3x. How do we do the derivative of secant of 3x? Well, we'll do that in a moment. We need next derivative of secant of 3x over there, and then over bottom squared. So our answer is this if we put the derivative of secant of 3x over there. So let's find on the side the derivative of secant of 3x with respect to x, because that's our variable. Well, if y equals secant of 3x, how do we take that derivative? We know how to take derivative of secant. The derivative of secant is given by secant tangent. But there's a 3x there. So let's write that 3x as u. So that y is now secant of u. This is all side work. This isn't another division. This is side work. Yeah, I'll keep doing it over here, I guess. So we have y is secant of u equals 3x. Then dy du is what? Secant u times tangent of u. Derivative of secant is secant tangent, so the derivative of secant of u with respect to u, secant u tangent u. Du dx, well, that's just the derivative of 3x, which is 3. So all of this work on the bottom was to find the derivative of secant of 3x, which we find by multiplying these two together. And we want to put that up here, so let's put that up here. Secant u tangent u times 3. U is 3x, so we have secant of 3x tangent 3x all times 3. So for this one we have bottom derivative top minus top derivative bottom all over. That's great, I just got this on the wall. All over bottom squared. That'll come off with a clean magic eraser. Bottom derivative top minus top derivative bottom all over bottom squared. What if we had this one? Y equals x squared minus 4x over secant x. What if we had this one? Now let's make it positive. What if we had this one all to the positive 4/7? Well, this is the same function as before. So we actually did a lot of the work we would need to do for this. So let's do this in one step. This is a function to the negative, to the 4/7. A function to the 4/7. A function to the 4/7. The derivative of a function to the 4/7, use power rule. 4/7 of them to the negative 3/7 using the power rule, and then you'd use a chain rule on the inside. But we have a thing to the 4/7, so the derivative will be 4/7 of them all to the negative 3/7. 4/7 minus 1 is negative 3/7. And then times the derivative of the inside. But we already did the derivative of the inside, so I'm just going to say times star like that, where star is the answer to the previous example. Star is the answer to the previous example. So here we had that function to the 4/7, the derivative is 4/7 of them to the negative 3/7, 4/7 minus 1, times the derivative of the inside, which we did in the previous example. If you have one, I mean, there won't be any on the test where I ask you, well, there will almost definitely be nothing on a test where I ask you something and then in the next question you would have to use it like that. But if I do, you could do that thing where star is the answer to something else on the test. And maybe I'll put them like 10 questions apart on the test. I don't know. Let's do this one now. E to the 4x. Well, we know the derivative of e to the x. Derivative of the x is itself. Derivative of e to the 4x, is it this? Is it itself? Derivative of e to the x is itself. So is this derivative itself? Well, no. Why is it not? Well, let's go through the details using a u substitution. We know how to take the derivative of e to the x, so let's let u be this entire exponent. Well, then what? dy du. Well, y is just e to the u, so dy du is itself from one of those rules. It was rule 7, one of the 22 rules. du dx, well, du, or u is 4x, so du dx is just 4. So then dy dx is these two multiplied, e to the u, there's e to the u, times 4. And you can write that as 4e to the 4x. By the end of the semester, I would guess most people will just write that as 4e to the 4x. But here, notice what the substitution does. The substitution shows that the derivative of e to the 4x is not just itself, because this is not just x. If that were just x, what? That would be 1, and it would be itself. But it's not just x, so we have 4 times e to the 4x. Notice here, with this one, derivative of e to the 4x was itself times the derivative of the exponent. And that is true from the details of that u substitution. So what if I change this question a little to e to the x squared plus cosine x? That's an e. E to the x squared plus cosine x. Well, we would do the same thing. dy dx is itself times the derivative of the exponent. And the derivative of the exponent we can find using the 22 rules. 2x and negative sine x. So the derivative of e to the x is itself times the derivative of the exponent. Here, if you did do a u substitution, that's good. My hand has marker all over. If you did do a u substitution, u would be x squared plus cosine x. How about this one? Y equals log of 14x squared plus 3x negative fifth. Well, we know how to take the derivative of log of x. So let's let u be that entire inside quantity, and then apply a chain rule. Let's let u be that entire inside quantity, and then dy du is what? Well, derivative of log u is 1 over u from rule 8, I believe. No, rule 9. Du dx, well that's another, well that's not a polynomial because that's a negative 5. But it's just a couple power rules. 28x, negative 15, negative 5 minus 1 is 6, so negative 15x to the negative 6. And then dy dx is these things multiplied. So it's these things multiplied. 1 over u is 1 over that, times du dx. That negative 5, maybe I should draw that fraction bar a little larger. That negative 5 is on that x in that denominator. And with this natural logarithm, I will simplify this to make an observation, and make an observation. Notice, if we just multiply these out, we have 1 over something times something. We can just write that as this in the numerator, and then that denominator is the same. So here, we could simplify that if we want. If we're asked to simplify it, that's how you would simplify it. Maybe you could do something. I wouldn't ask you to simplify by getting rid of negative exponent. But you could, notice you could write this answer like this. And what is this actual answer? Well, let's erase a lot of what's on the board. With a natural logarithm, the derivative is just, I was debating writing, yeah, I guess I'll write it in. The derivative is just using the chain rule given by the derivative of the top, right, the derivative of the inside all over the inside. So the derivative of the inside goes in the numerator, the inside goes in the denominator. And that works with natural log, and you can see the details using chain rule as we showed. maybe I should just say what this is equal. I shouldn't just write a fraction randomly. There, that fraction is the derivative of log of 14x squared plus 3x to the negative 5th. 1 over the inside times the derivative of the inside, which reduces to the derivative of the inside over the inside. That's a useful observation, which at the beginning of next week we will talk about in another application. Next, what about this one? 7 to the x squared minus 3x. Well, again, we know how to take the derivative of 7 to the x by Rule 8. But we don't know from those rules how to take the derivative of 7 to the x squared minus 3x. So we will get rid of that x squared minus 3x and replace it with u. Well, and then we can take dy du using Rule 8. Derivative of 7 to the u is 7 to the u, log 7, natural log. Du dx, well, derivative of that, that's just a polynomial. 2x minus 3. And then dy dx is these two multiplied. So 7 to the u, there's 7 to the u, times, let's say log, times the natural log of 7 times that. So we have dy du times du dx. Then you don't have to simplify that. Next, we haven't done any inverse trig, so let's do a couple inverse trig. Let's do this one first. The inverse sine of 4x squared. Well, the rules told us how to take the derivative of inverse sine. So let's make this look like just inverse sine by letting u equal 4x squared. That now reduces y to a function on which we can apply one of the first 22 rules, in particular Rule 17. Derivative of inverse sine is given by what? Is that one negative or not? Positive 1 over root 1 minus, in this case, u squared. Derivative of inverse sine is 1 over root 1 minus the inside squared by Rule 17. Du dx is just 8x by the power rule and the constant rule. Then dy dx is what we get when we multiply these. 1 over root 1 minus u squared. What's u? 4x squared squared. I'm not going to write the multiplication dot. So we have dy dx is 1 over 1 minus u, there's u squared, times 8x. And I am going to simplify this one a little. Just write it as one fraction. 8x over root 1. And I'm also going to square that thing. 8x over root 1 minus 16x to the 4th. Notice I squared the 4x squared. So here to use substitution gave us 1 over root 1 minus u squared times, in this case, 8x. And let's look at one final example. Let's do another inverse trig. And I'm going to do this one in one step. The inverse tangent of root x. Before doing it in one step, I'll say this after doing it in one step. This derivative is 1 over 1 plus x times 1 over 2 root x. Where did that come from? It might be a good idea to pause now and try to figure out where this came from. Where did it come from? Well, it came from two rules, the inverse tangent rule and the power rule. First, remember the derivative of the inverse tangent is 1 over 1 plus x squared. So, if this x is a root x, well, then we would get 1 over 1 plus root x squared, which is just x. So that gives us this first piece. But then the chain rule says to multiply by the derivative of the inside. The derivative of the inside, I did the shortcut. That's x to the half, so the derivative of the inside is half x to the negative half, which I just wrote like that for this example. You could have written, instead of this piece, half x to the negative half. But the chain rule says multiply by the derivative of the inside. If you want, the u substitution would be let u equal that inside, so let u equal root x. So these chain rule questions, it's very important, these questions in calculus. So definitely try the worksheet problems. It might also be a good idea to review the worksheet problems from last week. These are very important, and they definitely get easier with practice. When I first saw these, I found them quite confusing, but then, when you do a bunch of them, you start noticing patterns, and you start remembering certain things, and they definitely do become easier with practice. So in the next week, the next test is 3 weeks from, the Tuesday of this week, which is, I don't know the date of Tuesday of this week, whatever it is. Definitely get a good amount of practice in. I intentionally put chain rule kind of close to after the first test because it is something which, with 2 weeks of practice, definitely becomes easier to handle. So let me know if you have any questions. It's a very important topic.